Welcome back to Climate Dynamics. Today we're continuing our discussion of the oceans and focusing on the dynamics of the ocean. The reading for this is the second half of Marshall and Plum, Chapter 9. In this section, there's only a few definitions, analogous to what we saw in the atmospheric dynamics section. Here, the key definitions are the Taylor-Proudman theorem and Steric Effects. The three questions we aim to answer are: how does the concept of balanced flow from atmospheric dynamics translate to the ocean? How do the thermodynamic properties of the ocean determine its dynamical character? And what is the effect of temperature and salinity on sea surface height? Alright, let's get started with balanced flow. So the basic equations of the ocean are pretty similar to those of the atmosphere. The only deal is we need to replace the ideal gas law with the equation of state for the ocean that we discussed in the last lecture. Also, the continuity equation, which in the atmosphere describes how density changes as a function of time, is replaced by a more simple relationship, which is effectively that the divergence of the velocity is equal to zero. This naturally emerges from the continuity equation if you fix the density as constant. It's an approximate relationship that effectively holds for incompressible fluids. The idea being that if a fluid is incompressible, then you must have no change of volume, and with no change of volume, you must have zero divergence associated with it. Alright, so with this in mind, we know that much of the basic principles from atmospheric dynamics can then be carried over. The only difference being that we're going to have to use a new thermodynamic principle. Okay, and that thermodynamic principle, of course, comes from the seawater equation of state that we discussed last time. Here it is again for review, but recall the basic idea is that the density is equal to some base density plus variations due to temperature and differences due to salinity. This is again an approximation of the actual equation of state that is obtained through a Taylor series expansion. More complicated equations of state can of course be used as necessary depending on how much accuracy is needed for your particular calculation. For the purposes of this class, however, this simplified equation of state is sufficient enough. Okay, let's go back to discussing hydrostatic balance. Now, recall that hydrostatic balance basically emerges from the vertical momentum equation when we have zero vertical velocities. So this equation is the same in the ocean as it is in the atmosphere. Under hydrostatic balance, W is equal to 0, so the left-hand side of this equation is 0, and so we can solve to show that the vertical gradient of pressure is going to be equal to negative rho times g. If we write rho in terms of the density anomaly, recall this is rho reference plus sigma, where sigma denotes the density anomaly, we then obtain the equation on the bottom of this slide. If we neglect contributions from sigma, because of course they're fairly small relative to the reference density, then the equation can be integrated directly. Namely, we just see on the right-hand side basically a constant equal to negative g times rho reference. Integrating this then gives us an expression for a pressure experienced at a particular depth as a function of the surface pressure. Now, the surface pressure at the ocean is, of course, the atmospheric pressure that is experienced above it. Recall in our discussion of hydrostatic balance for the atmosphere that the pressure at a particular point on the surface was basically equal to the mass of atmosphere above you. In the ocean's case, this is naturally extended to depth, namely, the total pressure that you experience is equal to the mass of atmosphere above you plus the mass of ocean water above you. Since the density of ocean water is approximately constant, then pressure simply varies linearly as you go to depth. Namely, the pressure as a function of depth is equal to the surface pressure minus g rho reference times z minus eta, where eta here denotes the height of the free surface above the z equals 0 point. This height above the free surface does vary depending on position, and it does play a role in then affecting the underlying pressure. Variations in sea surface height then can result in horizontal variations in pressure. Because this variation in sea surface height, of course, results in more or less mass of ocean water located above you at any position. So note in particular that there's a linear dependency of the pressure with the depth within the ocean. This compares to this is very different than what we saw in the atmosphere. Recall in the atmosphere, for a constant temperature profile, we had an exponentially decaying pressure as one went up in altitude. However, here, what we are seeing is a linear increase in pressure as we go to deeper depths. Note here, and throughout the remainder of this lecture, we're going to use a coordinate z denoting depth that is 0 at the surface and goes to increasingly negative values at depth. Thus, this coordinate z agrees with what we've been using in our atmospheric analysis to date. Okay, so taking this equation for hydrostatic balance as a function of position, we have that the pressure at a particular position is equal to atmospheric surface pressure minus g rho reference times the distance between the current depth and the free surface height. So the pressure at a depth of 1 kilometer in the ocean is thus about 10 to the 7 pascals, or about 100 times atmospheric pressure. Pressure increases fairly rapidly in the ocean because of the density of seawater is significantly larger than that of air. Consequently, you have much more mass of seawater above you under a very short depth as opposed to being on the surface. Note, however, that this minus g rho reference z part of the pressure is effectively dynamically inert. That is, it does not drive horizontal dynamical circulations at constant depth. Think about it this way. Basically, in the horizontal momentum equation for the ocean, we have gradients of pressure along constant z surfaces. If z is held fixed, then the term minus g rho reference times z is of course going to be constant. Taking the gradient of this term then results in a 0 horizontal derivative. Thus, the only thing that triggers horizontal variations in the pressure, that is, non-zero pressure gradients along constant z surfaces, are variations in the surface pressure and variations in the surface height. Again, this equation was derived assuming that sigma, or density anomalies, are small. We'll see later that if we do not neglect sigma, then we can still get horizontal pressure gradients that emerge because of horizontal variations in temperature or salinity of the fluid. Okay, recall back to lecture 4a and 4b that we discussed buoyancy in the atmosphere. Our discussion led to the derivation of a second-order ordinary differential equation for the displacement of a fluid parcel from some reference location, as shown here. What we found was that when this constant coefficient term in front of the delta z was greater than 0, we had solutions that were sinusoids. Consequently, in this case, we had a stable atmosphere where small offsets of a fluid parcel from its initial position would simply lead to oscillations of that fluid parcel about its neutrally buoyant altitude. This gave rise to the definition of the Brunt-Väisälä frequency, which was basically that n squared, which is the square of the Brunt-Väisälä frequency, was equal to g times the difference between the dry adiabatic lapse rate and the environmental lapse rate, all divided by the temperature at the reference altitude. The solution then was sinusoidal or oscillatory in terms of this Brunt-Väisälä frequency. In the ocean, the problem is a bit simpler. Namely, because we don't have changes in the volume of fluid parcels as they move up and down, or at least very small changes compared to what we saw in the atmosphere, buoyancy instead relies simply on the density of the fluid parcel. Namely, in the left-hand side of the figure shown here, we have a stable arrangement where you have higher density fluid underlying lower density fluid. This is the case in the atmosphere as well, where we have stability. However, in the atmosphere, because density was not a conserved property of fluid parcels, that is, because we didn't have that the material derivative of density was equal to 0 in the atmosphere, it was more difficult to use it as a property to deduce the buoyancy of fluid parcels. Instead, we found that potential temperature, which was a quantity that was conserved following fluid parcels, provided a better description of whether the atmosphere was stable or unstable. On the right-hand side here, we see an unstable arrangement within the ocean. In this case, we have lighter fluid underlying more dense fluid, or heavier fluid. In this case, the arrangement is unstable and will give rise to an exchange of the positions of these two fluid parcels. That is, the lighter fluid will tend to rise and the denser fluid will tend to sink. The consequence is the development of Rayleigh-Taylor instability, or convective cells within the ocean. This particular arrangement is very rare, typically only occurring in the deep Arctic or polar regions of the ocean. This is because, since the ocean is heated from above, the tendency is to have lighter fluid sitting over top of denser fluid, or a stable arrangement. The only way in order to produce the unstable arrangement on the right is if we have some sort of sensible or latent heat flux from the top of the surface, or other form of radiative cooling that results in then cooling of this near surface layer. Alright, consider now how the acceleration of the fluid parcel will be affected by vertical variations in density. Since we know that the buoyant acceleration is equal to minus g times the difference between the density of the fluid parcel and the density of the environment, we can use a Taylor series expansion to show that the buoyant acceleration experienced for a fluid parcel displaced by a distance delta z from its initial location is given by the equation on the bottom. Taking this and plugging it in to our second order differential equation for the displacement delta z then gives the expression on the top. Here we again see an equation that looks very analogous to what we saw in the atmosphere for small displacements of an initial fluid position. In a stable ocean, where we get trigonometric or sinusoidal solutions of this differential equation, we must have that g over density of the environment times the derivative of the density of the environment in the vertical direction must be less than 0. That is, when you take the second derivative of the delta z term, you get negative of the initial delta z. This, of course, then corresponds to these trigonometric or sinusoidal oscillatory solutions. The Brunt-Väisälä frequency in the ocean that then emerges from this particular stability requirement is then given by the expression shown in the bottom left here. Namely, the square of the Brunt-Väisälä frequency is equal to negative g over rho environment times the vertical derivative of sigma. The units of this are seconds to the minus 2. So the Brunt-Väisälä frequency in the ocean works effectively the same way as it does in the atmosphere. Namely, it indicates the period of oscillation of fluid parcels that are displaced from their initial location. If the square of the Brunt-Väisälä frequency, or rather if this right-hand side term ends up being negative, then the ocean is not stable and the fluid parcel will rise without bound. In that case, we get exponential solutions to the differential equation shown on the previous slide. We can estimate the Brunt-Väisälä frequency for the ocean and hence understand the approximate oscillatory frequency for fluid parcels in the ocean by looking at variations in the density anomaly sigma. Let's for a moment assume that this density variation is purely a function of the temperature of the background fluid. Plugging in our equation of state that we had earlier, we then can replace the di sigma di z with a di t di z term, bringing in the alpha t term, which describes the thermal expansion coefficient of water. In the near surface layer, this quantity is approximately equal to 2 times 10 to the minus 4 1 over Kelvin. Using a temperature difference of about 15 degrees Celsius over a distance of 1,000 meters, one can then calculate the Brunt-Väisälä frequency as 5 times 10 to the minus 3 1 over seconds, or about a 20-minute period of oscillation for these fluid parcels. All right, let's go back to the horizontal momentum equation. The horizontal momentum equation in the ocean is of course analogous to its atmospheric counterpart. Acceleration is shown on the left-hand side here. This also captures curvature associated with the flow. The pressure gradient is the same, the Coriolis is the same, and the ocean also experiences frictional forces. The length scale in the ocean is determined by the size of typical ocean gyres, which are about 2,000 kilometers. However, the flow velocity of the ocean is also much smaller than it is in the atmosphere, with a typical flow velocity of about 10 centimeters per second or about 0.1 meters per second. Plugging these into the expression for the Rossby number, we have a Rossby number in the ocean of about 10 to the minus 3. This is of course much smaller than the atmospheric Rossby number, which we calculated to be about 0.1. This means that in the ocean, approximations such as thermal wind and geostrophic balance actually are excellent and hold even much better than they do in the atmosphere. For small Rossby numbers, the curvature of the flow can typically be neglected, and so the dominant balance in the ocean is again between pressure gradient, Coriolis, and frictional forces. Recall in our discussion of the atmosphere, this contribution gave rise to geostrophic flow away from the surface and subgeostrophic flow in the near surface. The same thing holds in the ocean. We have regions where geostrophic flow is dominant, and in the near surface we have a region where subgeostrophic flow is dominant, and we have an Ekman layer that is naturally present within the oceans. We'll discuss this in more detail as we talk about the wind-driven circulation. So in the ocean, the geostrophic wind is defined analogous to how it is in the atmosphere. Namely, we have components of the geostrophic wind given by minus 1 over F rho reference times a derivative of pressure perpendicular to the component of the flow that we're assessing. Since density varies very little through the ocean, one can typically replace the density in the denominator of the geostrophic flow with the reference density. This makes some of these calculations a little bit simpler. Alright, let's use this definition of geostrophic wind in order to derive the thermal wind in the ocean. This then allows us to relate horizontal velocities to horizontal variations in the thermodynamic properties of the ocean, in particular pressure, density, and salinity. Note that this is of course not a real wind since we're dealing with ocean flows, but we can nonetheless refer to it as such. This allows us to also draw parallels with what we saw in the atmosphere. Alright, let's take these expressions for the geostrophic flow that we had in the ocean from the previous slide. We can differentiate these both with respect to z in order to understand how the geostrophic wind then varies in the vertical direction. Since f and rho reference are independent of z, this allows us to pass this derivative directly through. We can then exchange the order of the derivatives and substitute in the hydrostatic relationship that we had talked about earlier in this lecture. This then allows us to relate vertical variations in the geostrophic flow velocity to horizontal variations in the density anomaly sigma. Thus, these horizontal variations in density anomaly, again prompted by variations in the sea surface height or variations in temperature or salinity, can give rise to variations in the geostrophic flow velocity. Let's see if we can then use this concept in order to assess what the typical flow directions are within the ocean. Recall we had done a similar exercise to this for the atmosphere. In the ocean, actually, it turns out to be much simpler. Here's a cross-section of potential density within the ocean. Recall that the thermal wind relationship that we had for the ocean is related then to the meridional variations of the density anomaly. In this case, we're going to derive the zonal velocities of the ocean at the surface using meridional variations of the density field. Okay, the first thing we need to do is we need to calculate meridional derivatives of the density anomaly. Let's pick a few typical cross-sections through the ocean and then assess over those cross-sections what the value is or what the sign is of di sigma di y. On the left-hand side, we're going to pick a subpolar cross-section, we're going to pick a subtropical cross-section, and analogously in the northern hemisphere. If we approximate at the bottom of the ocean that geostrophic flow is approximately zero, which is typical because the ocean quickly goes towards homogeneous thermodynamic properties at depth, hence giving rise to essentially zero pressure gradient in the horizontal direction, it's a very good approximation to have zero flow velocity at depth. We can then integrate this equation for the thermal wind from the bottom of the ocean up to the top in order to estimate the flow velocities at the surface. Alright, so looking at this plot of potential density, we can see on the far left-hand side that as you go from the polar regions towards the subtropics, we have that density decreases. Consequently, we have di sigma di y along this cross-section is negative. And the same thing holds regardless of how deep you go. If we look at the subtropical cross-section, namely between about 20 degrees south and about 10 degrees south, here we have that in fact the density gradient reverses, namely you go from less dense fluid around the subtropics to more dense fluid in the equatorial regions. Recall again that this is because of Ekman pumping and suction that occurs in these equatorial and subtropical regions. However, this gives rise then to this positive gradient of sigma at this particular cross-section. In the northern hemisphere, we see a decrease of the density going from the equatorial band towards the subtropics. Then, as we get out of that subtropical region, we see an increase in the density as we go into the polar regions. And then finally, in the deep polar regions, north of about 60 degrees north, we actually see a decrease again in the density at depth. However, in this case, it's fairly weak. So the question is, with this knowledge in hand, can you then estimate the positions of the major east-west ocean currents? Well, let's just integrate these from the bottom of the ocean up to the top, noting that the same sign is present through each of these cross-sections. If we do that, and if we apply the presence of the Coriolis parameter, f, noting that it is negative in the southern hemisphere, what we have then is that the geostrophic flow at the surface must be opposite to the sign of di sigma di y in the southern hemisphere, and it must be aligned with the sign of di sigma di y in the northern hemisphere. So in particular, at about 50 degrees south, we have flow that is from west to east. At about 20 south, we have flow that's from east to west. At about 20 north, we have flow again from east to west. In the mid-latitudes, at about 45 degrees north, we have flow from west to east. And then finally, in the polar regions, we have weak flow that goes from east to west. Note that this methodology can't be applied near the equator where the Coriolis parameter goes to 0, because of course the equation below becomes singular at that point. However, we're going to investigate this particular location in more detail in 2 lectures' time. So how does this assessment compare to our observations of global ocean currents? Well, if we look back at our figure describing global ocean currents, what do we see? Well, we see in the far south we have westerly flow. That is, the Antarctic circumpolar current is associated with flow from west to east, whereas the south equatorial current, south of the equatorial band, is associated with flow from east to west. This is part of these large-scale ocean gyres. In looking farther north into the northern hemisphere, we have the north equatorial current associated with flow from east to west, and then going north of that, we have flow from west to east. The polar circulations are not shown with deep red or deep blue arrows here, but you'll notice a very weak easterly circulation that is nonetheless present in these deep polar regions. So it seems as though this analysis that emerges from the thermal wind balance actually works quite nicely in the oceans and gives us the currents that we would expect. All right, we can also use the thermal wind relationship to estimate the mean surface geostrophic flow. Assuming abyssal currents are weak, that is, the geostrophic flow goes to 0 at depth, we can then essentially integrate this equation over the distance of about 1,000 meters in the ocean, giving us our vertical length scale, and use the previous plot in order to estimate the variations in the density anomaly with length. So if we assume a typical length scale of about 2,000 kilometers and estimate the density anomaly along that distance in the meridional direction, such as between 20 north and 40 north, we get a density anomaly of about 1.5 kilograms per meter cubed. Plugging that then into this relationship and estimating the surface velocities at 30 north then gives us an estimate of about 8 centimeters per second for the typical surface current velocities. So that's not too far off from what we actually observe for typical oceanic flows. In the previous discussion of thermal wind, we assumed that density could vary in the horizontal direction. If density was unable to vary, we would actually find that the thermal wind was equal to 0, which would of course imply that the geostrophic wind could not vary with height. This basic result is the basis for what is known as the Taylor-Proudman theorem. Namely, if flow is geostrophic and homogeneous, that is, if density is constant, then the flow is actually two-dimensional and does not vary in the direction of the rotation vector. This proof follows very analogous to the previous derivation of thermal wind, except here again we assume that the density anomaly in the horizontal direction is equal to 0. If that were the case, and starting from the geostrophic flow velocities that we had derived from the balance of Coriolis and pressure gradient force, assuming ρ and f are constant, we could then differentiate these expressions in the vertical direction, again flip the order of differentiation, and plug in pressure equals, or di p di z equals negative ρg. Since ρ and g are again constants, derivatives of these in the horizontal direction are 0, and so the derivative of the geostrophic wind in the vertical direction must also be equal to 0. So in the case of constant density, we must have 0 geostrophic flow in the z direction. So it's fortunate that we do have this density anomaly in the background state, Otherwise, we wouldn't be able to have surface currents that emerge from this integration through the ocean depth. A more general proof of the Taylor-Proudman theorem emerges from the vector form of the dynamic equations for the ocean. In this case, the right-hand side is equal to 2 omega cross u, where omega is the vector pointing in the direction of the rotation axis. This term represents Coriolis forces, plus 1 over rho times gradient of P, which is the pressure gradient force, minus gradient of Gz, which is the gravitational force. All of these must balance each other for a flow with du dt equal to 0. If we take the curl of this expression and use the fact that the divergence of the geostrophic wind is equal to 0, and the curl of a gradient is equal to 0, this then yields a simple result, namely omega cross gradient of u is equal to 0. So, in other words, u cannot vary in the direction of the rotation vector. So what does this mean in practice? Well, consider a rotating flow. In this case, we can simplify the domain of the experiment by considering, for instance, a cylindrical fluid tank that's rotating on top of a turntable. In that case, we must have that the flow is effectively two-dimensional. That is, regardless of how deep you are in the flow, you will have the exact same flow velocity. So for slow, steady, frictionless flows, the wind vectors or the flow vectors do not vary along this direction of rotation. Vertical columns of fluid that then emerge from this study remain vertical and undisturbed. These vertical columns of fluid then, although they can shift position and deform around the tank, they cannot be tilted. That is, the velocities are the same regardless of depth. This can actually be seen in an experiment. Consider, for instance, this rotating fluid tank where we have placed a cylindrical obstacle on the bottom of the tank. Because the flow above the cylinder must be preserved, we then have that any flow encountering the cylinder must go around the cylinder. Otherwise, it would disturb the flow on top of the cylinder and result in a flow that is three-dimensional. Although this experiment could easily be conducted at home, fortunately, we have professionals that have conducted it for us and recorded the video on YouTube. You can follow this link in order to see these Taylor columns in practice, taken from a video made by the Spin Lab at UCLA. What we see in this figure is a green dye that has been injected into a flow that has been spun up on a turntable. What we see is as this flow evolves in time, the green dye will actually avoid the region over top of the cylindrical obstacle. That is, the Taylor column that is present over this cylindrical column prevents a flow from moving in and disturbing the local flow. Thus, the flow maintains its two-dimensional character. Okay, let's talk about two different flow regimes within the ocean, both near-surface flow and flow at depth. Consider a fluid parcel in the Gulf Stream that's being transported approximately eastward. In order to compensate for the southward directed Coriolis force that the fluid parcel is experiencing, there must be a pressure gradient force that is directed northwards, opposing that Coriolis force. So where does this pressure gradient force come from? To understand where these horizontal pressure variations come from, consider back to our expression for hydrostatic balance of the ocean. This expression relates vertical variations in the pressure to the density field. We can integrate this expression from some depth z to the free surface, which occurs at z equals eta. Eta here is the height of the ocean's free surface and varies in the horizontal direction. By doing so, we can then express the pressure at depth z in terms of the surface pressure and a term equal to g times the mean layer density times the distance between the free surface height and the depth z where we are performing this calculation. The mean layer density expression is shown here in the bottom right. So what does this mean? Well, we have a free surface that varies in terms of its height, or analogously, the depth that we have within a fluid is a function of the height of the free surface above us. The higher the free surface, the higher the pressure that we're experiencing because we have more fluid that overlays us. Analogously, as the free surface dips down, we have less oceanic fluid that overlays us, and consequently we experience less pressure. Thus, in the near surface regime, along lines of constant depth, that is, where z is held constant, the horizontal variations in the pressure are going to be dominated by the variations in this surface height. In this regime, the horizontal variations in the mean layer density are small, and so we can neglect that mean layer density variation and replace it simply with the reference density. So ignoring these gradients in atmospheric surface pressure, since they occur on much shorter timescales, we then have that horizontal variations in the pressure that are experienced in the near surface are largely given by horizontal variations in the sea surface height. Plugging this expression for the gradient of pressure into our expression for geostrophic balance, we then have that the vector geostrophic wind in the near surface is going to be equal to g over f times k cross the gradient of the free surface height. Or in component form, we have the two expressions shown at the bottom here for the near surface geostrophic flow. In the atmosphere, geostrophic winds of about 15 meters per second are associated with tilts of pressure surfaces of about 800 meters over distances of about 5,000 kilometers. However, we've already seen that oceanic flow is much weaker than it is in the atmosphere, and so we also expect to see much gentler tilts of the free surface. So, given this expression for the geostrophic flow above, and knowing a typical value for geostrophic flow of about 10 centimeters per second, or about 0.1 meters per second, we can estimate typical variations in the free surface height. Plugging in u equals 0.1 meters per second, f equals 10 to the minus 4, 1 over seconds, and length scales of about 10 to the 6 meters, as well as g approximately being 10 meters per second squared, we can then calculate this variation in free surface height. I'll give you a moment to think about what that value might be. What we expect is to have about 1 meter of free surface height variation then over this distance of 10 to the 6 meters, or about 1,000 kilometers. This is pretty typical in the ocean, and enough in order to give rise to geostrophic flows of 10 centimeters per second. Does this agree with what we see in reality? Here's a plot showing sea surface height anomaly from the mean sea surface height over the planet. Regions that are blue correspond to regions with higher free surface heights. Regions that are brown correspond to regions with lower free surface heights. Where we see sharp variations in those free surface heights are also regions where we expect to see strong geostrophic flows because of strong gradients in the free surface height in the near surface layer. Is this estimate of about 1 meter of free surface height reasonable? Well, given that these are centimeters for the scale shown below, this is not actually a particularly bad estimate, particularly over the length of the Gulf Stream. All right, let's consider the alternative flow regime, that is, geostrophic flow at depth. In this regime, horizontal variations in mean layer density can no longer be neglected compared to those of column depth. So let's go back to our expression for pressure at arbitrary depth z. We're going to take the gradient of this expression again, but in this case, even ignoring variations in atmospheric surface pressure, we get a two-term expression for the gradient of P in terms of variations in the free surface height and horizontal variations in the mean layer density. In order to calculate the geostrophic flow velocity, we need to calculate K cross this gradient of pressure, which then applies basically the K cross to each of the gradient terms on the right-hand side. The flow velocity then emerges naturally. Namely, if we take that K cross gradient P term and divide by F rho reference, we then get the geostrophic flow velocity vector. A simplification can be made by noting that the mean layer density is approximately equal to the reference density. This allows us to simplify this expression somewhat and gives us the final expression shown here in the bottom. This expression then provides an accurate estimate for geostrophic flow in the interior ocean, far below the near surface layer. Observe from this expression that if density was uniform, that is, if there were no horizontal gradients in the mean layer density, that the geostrophic velocity would purely be a function of the free surface height and is actually independent of depth. This is not what we observe in reality, however. In practice, the geostrophic velocities are very small at depth. That is, flow tends to be very close to zero, as we saw before in our assumption of zero abyssal geostrophic velocities. Consequently, it must be the case that these two terms approximately balance each other in practice. If this is the case, namely if the geostrophic flow at depth is nearly zero and the two terms approximately balance each other, then we must have, by taking the magnitude of these two terms, that the height of the column divided by the reference density times the magnitude of the horizontal variations in the mean layer density must be approximately equal to the magnitude of the horizontal variations in the free surface height. If we divide this expression through by the square of the Brunt-Väisälä frequency, then we can actually see from this expression that the magnitude of the isopycnals, that is, surfaces of constant density, must be approximately equal to g over the Brunt-Väisälä frequency squared, also divided by the column height, times the magnitude of the free surface variations, or in other words, the free surface slope. That means that in practice, with a Brunt-Väisälä frequency of about 5 times 10 to the minus 3 1/seconds, and a height of the column of 1 kilometer, we must have that for every meter the free surface tilts up, the density surfaces must tilt down by approximately 400 meters. That means that these density surfaces can have quite sharp slopes associated with them because of small variations in the free surface. Is this something we see in practice? Indeed, it turns out that this is the case. In the subtropical regions, we typically see positive variations in the free surface height. That is, the free surface tends to be pushed up. In subpolar regions, instead, we see a depression in the free surface height. This does make sense from a thermodynamic argument as well, because in the subtropics, warmer underlying fluid is then responsible for taking up more volume and consequently pushing up the free surface, whereas the colder waters of the subpolar region require less volume and so pull down the free surface. The isotherms, that is, lines of constant temperature, are plotted here. Note that the colder isotherms at depth appear closer to the surface in the subpolar region and appear at depth in the subtropical region. In this figure, warm subtropical columns of fluid are expanded relative to the colder polar columns. Thus, the sea surface is higher in these subtropical regions, by about 1 meter in the subtropics than they are in the subpolar regions. The pressure gradients that are associated with this free surface height are then largely able to compensate for variations in temperature that occur at depth. Consequently, the abyssal circulation ends up being much weaker because of the compensating influence of the thermal variations and the free surface height in the ocean. This is again observed in practice. Here we see a depiction of sea surface height at each location over the surface using a 10-year mean climatology. This sea surface height variation indicates positive sea surface height anomalies occurring in the subtropics regions and negative anomalies in the polar regions. Again, this is associated with warmer underlying waters in the subtropics that are then responsible for taking up more volume, and colder, more dense waters that occur in the subpolar regions that take up less volume. We can also see this in the zonal cross-section of the potential density field. Observe in the subtropical regions, we have lower potential densities associated with fluid taking up greater volume. In the polar regions, on the other hand, we have higher potential densities associated with colder, denser fluid. In the regions where the column average potential density is low, we also require that the fluid takes up greater volume, hence leading to an increase in the free surface height in these regions. Recall that we had said earlier that a 1 meter variation in the free surface height must correspond to approximately a 400 meter change in the depth of a constant density surface. That is actually exactly what we observe in the real oceans. Namely, in the subtropics regions, in order to get to a depth of approximately 1026.5 kilograms per meter cubed, we must go significantly deeper than we must in the polar regions. Over this region, namely between the subtropics and the subpolar regions, we have a variation of about 1 meter of surface free height. This corresponds to a change in the depth of this density surface of approximately 400 meters, as shown in this figure. As we've seen, variations in the height of the ocean are a function of variations in the underlying density of the ocean water. These variations in density then also give rise to variations in fluid flow velocity. However, the density of the ocean water is also controlled by variations in temperature and salinity. Namely, we know that warmer ocean waters are responsible for less dense fluid. This then it pushes up the free surface height. However, salinity is responsible for shorter fluid columns because it drives up the density of the ocean water. The expansion and contraction of these water columns, due to both temperature and salinity anomalies, is known as the steric effect within the ocean. In order to assess this steric effect, we can use our expression for relating the horizontal variation in the mean layer density to the horizontal variation in the free surface height. Using our averaged equation of state, we can plug in the expression for the horizontal variations in the mean layer density and then decompose the magnitude of this term into variations due to both temperature and salinity. Going through this short derivation, we find that the variations in the free surface height divided by the height of the fluid column are approximately equal to the thermal expansion coefficient of the water times the temperature variation minus the effects of salinity on density times the salinity difference. Over the meridional extent of the subtropical gyres, we estimate that the temperature difference is about 10 degrees Celsius. This is fairly consistent throughout the oceans. The salinity variations can be deduced from the zonal cross-sections of the salinity. What we see over the meridional extent of these subtropical ocean gyres is that the difference in salinity is approximately half a practical salinity unit. So if we plug these two terms into the expression for variations of the free surface height, what we find is that the temperature expansion is approximately responsible for about 2 meters of total expansion over the subtropical gyre, and salinity is responsible for driving a contraction of about minus 0.38 meters. So over the top kilometer of the ocean, the height variations due to salt are more than offset by approximately 2 meters of total thermal expansion. Here we see, again, the reported mean height of the sea surface relative to the geoid, contoured every 10 centimeters. So the variations in this height profile are then associated with variations in temperature and salinity at depth. The dominant contributor to this variation in free surface height is the temperature in the system, but salinity is a non-negligible influence as well. Alright, that's all for today. Thank you very much. Next time we'll be getting into the wind-driven circulation.